Okay, so now we have three ways to solve systems of equations. We can use elimination, substitution, or graphing. But how do you know when to use which? So you should use elimination when each variable has a number in front of it, or a coefficient. So in this example, oops, forgot my plus sign. It would make the most sense to use elimination because both variables have a coefficient in both equations. So we would have to rearrange them to standard form, and I would probably multiply this equation through by 2, negative 2, to eliminate one or both of the variables. We're going to use substitution when one variable is easily isolated. So in this example, the coefficient on y is 1, so it's easily isolated. So you would just subtract 4x from both sides to solve for y, and then substitute that expression in for y in the second equation. And we're going to use graphing, well, when there's a graph. Remember, when solving by graphing, it's really important to be precise in order to get a correct solution. Okay, let's think about the following situation. Factory has machines that produce toys. Toys are then packed by the factory workers. One day, each machine produced 14 toys. And each worker packed 2 toys, so that a total of 40 toys remained unpacked. Additionally, the number of workers that day was 8 less than 7 times the number of machines. How many machines and workers were there? Well, let's start by defining our variables. Let's call M the number of machines and W the number of workers. So we know that each machine produced 14 toys. Okay? And then each worker packed 2 toys. And a total of 40 remained unpacked. So that unpacked is going to tell us that we subtract. And then we know that the number of workers that day was 8 less than 7 times of the number of machines. So 7 times the number of machines less 8. Okay, so which method should we use to solve this system? I hope you're all yelling substitution at me because we have one equation already solved for W. So we substitute this stuff in for W in the first equation. Now, if you work this out, you'll find that you get this. 16 equals 40. There's a problem. No solution. Okay, let's look at another example. All right, let's try solving this system by all three methods that we know. If we use substitution, we'll have to solve one equation for one variable. So we can solve the first equation for y, getting y equals x minus 3, and then substitute this stuff in for y in the second equation. So you get negative x plus the quantity x minus 3 equals 2. Let's pause there and look at how we would do it by elimination. The coefficient on all the variables is 1 or negative 1. And x, it's both negative 1, and y, it's both 1. So if we multiplied one equation through by negative 1, we could add them together and eliminate a variable. So multiplying the second equation through by negative 1 gives us x minus y equals negative 2. And then we would add the two equations together. Have the guest teacher pause the video and you guys graph the two equations. Uh-oh, our lines are parallel and they never intersect, which is why when you solved out either our substitution or our elimination, you would get no solution. What would have been a clue that that was going to happen? If you said that the coefficient on the two x terms was the same, you would be correct. That means that they have the same slope. Okay, let's look at this example. First, let's start by trying to solve it by elimination. So our equations are already in standard form, and the variables are stacked up in columns. What would be an obvious way to eliminate one of the variables? If we multiply our first equation through by 2, then we'll have a positive 2y and a negative 2y. So multiplying the first equation through by 2 gives us 6x plus 2y equals negative 2. And when we add our equations, both variables fall out. Because 6x minus 6x is 0, and 2y minus 2y is 0. And negative 2 plus 2 is 0. So our solution is infinite. Have the guest teacher pause this video and you guys graph it to verify that that's true. When you put your equations into slope-intercept form to graph them, you'll find that they are actually the same equation. So again, this system has infinite solutions. Okay, let's look at the shopping problem. So Mr. McNeely is going to quit his day job and become a farmer. He decides to buy a field and divide it between broccoli and spinach crops. Last year, the farmer of the field grew 6 tons of broccoli per acre and 9 tons of spinach per acre, for a total of 93 tons of vegetables. Mr. McNeely is not a very good farmer and also likes to spend his time playing video games, so he doesn't think he will be able to grow that much. He thinks he will be able to grow 2 tons of broccoli per acre and 3 tons of spinach per acre, for a total of 31 tons of vegetables. How many acres of broccoli crops and how many acres of spinach crops does Mr. McNeely have? Well, let's start by defining our variables. Let's call B broccoli and P spinach. So let's write our equation. So last year, the farmer grew 6 tons of broccoli and 9 tons of spinach, for a total of 93 tons. Mr. McNeely is going to try and grow 2 tons of broccoli and 3 tons of spinach, for a total of 31 tons. There's our system. Which method do you think we should use to solve this system of equations? I think we should use elimination. If we multiply our second equation through by -3, we'll get -6b, and our b's will cancel. So multiplying through by -3 gives us -6b minus 9p equals -93. When we add our two equations together, the b's cancel, the p's cancel, and we end up with 0 equals 0, which means it's an infinite solution. Any ordered pair would work. Can you think of one? I'll see you guys next week.